So this 10.1 lecture worksheet. And this is the conversion tables for standard kitchen conversions. Mostly you are trying to use these standard measuring instruments like a teaspoon. TSP is a teaspoon. That's the small one compared to a TBSP. That's usually a lowercase t versus an uppercase T. That's a tablespoon. And so you can see that 3 teaspoons fit into 1 tablespoon. Okay. And so those are your most common tablespoons and cups. This is a cup. Okay. So this is the most common measurement in my own kitchen too. And so you can take anything from one column, like 3 teaspoons equals 1 tablespoon, or you can take 48 teaspoons is equal to 16 tablespoons, which is so anything in one column is equal to another column when you're looking for converting from one unit to another. Okay, so it's just a matter of finding the units. So when they're asking us how many tablespoons are in 2 cups of water, so we need both tablespoons, and so I can use this tablespoons and cups. Let's use a different color actually. So this is tablespoons and cups. And if I'm going to convert from 2 cups to cancel out. So I need the cup to be on the bottom. And so ideally, it's best to have the 1 on the bottom so that that makes the numbers equal. So I'm going to choose this 1 cup is equal to 16 tablespoons. So 1 cup is equal to 16 tablespoons. And that makes the numbers easiest, okay? Because you could have chosen any of these. You could have chosen 3/4 cup is equal to 12 tablespoons, or 1/16 of a cup is equal to 1 tablespoon. As far as calculations, I don't have to use a calculator. If just 16 times 2, that's going to be 32 tablespoons. Okay. And I mentioned in the video that for these, the rounding is not going to be done to decimals for cups, because most of the time you don't have fractional. You have 1/4 cup, you have 1/16, 1/8 of a cup, 1/2 of a cup, but you don't have 0.2 cups. Okay. So that's the thing about the cup measurements is you notice that they are in fractions that are not decimal values. Okay, so that's what you'll notice is rounding is not going to be necessarily happening, because cup measurements they're very specific for 1 cup, 1/2 cup, and so on. Okay, so let's look at the next one, which is what is the volume in milliliters of 2 cups of. Okay, so again, you have 2 cups of water, and we want to convert this to milliliters. Okay, so now I know from all of these up here that I have cups, but I don't have any milliliters. I've got teaspoons, tablespoons, fluid ounces, pint, quart, and gallon. But down here, I do have cups to milliliters. So this in these two, this is good for liquids, these milliliters, cups to milliliters. And again, I can choose 1/4 cup equals 60 milliliters, any 2 numbers from those 2 columns. But ideally, what I want in this conversion factor is the cup on the bottom so that I can cancel it out. Actually, I cancel that, so let me cancel. So I want to cancel cup and cup. So what I'm going to choose is the number that is 1 cup and how many milliliters is equal to, because having 1 on the bottom makes the numbers easiest for calculations. So that 1 cup is equal to 240 milliliters. And so this is going to be 480 milliliters. Okay. Okay, so for number 3, this is looking at what is the mass in grams of 2 teaspoons of water. So this time I have 2 teaspoons, that's TSP of water, and I want teaspoons on the bottom, so TSP on the bottom, and I want that to go to grams. So what have I got here? Let's clean this up a little bit. and see that I can go from here is teaspoons. But this does not convert to grams. So I can go to tablespoons, fluid ounces, cups, pints, quarts, or gallons, but it doesn't go to grams. And I don't have any help here, but I do have help or grams. So that's grams or G. The thing is there's no teaspoons on there. So the grams can be converted from ounces or pounds. And so I guess the connection I'm finding that is similar in both of these charts is that grams get to through ounces. So see, I just circled that in purple. I can go from teaspoons to these ounces. These are fluid ounces. And then from fluid ounces, I can go to grams. So I'm going to use two conversion factors. So the two conversion factors are going to come from those two separate tables. And so this is 2 teaspoons of water. So a teaspoon on the bottom. And so let's find this teaspoon to fluid ounces. I don't have a 1 teaspoon, so I'm going to just choose this top one. 3 teaspoons is equal to 1/2 fluid ounce. Okay, so that's a fluid ounce or just an ounce OZ. So OZ is an ounce. And it's also the same as a fluid ounce. FLOZ is the same as OZ. So this ounce water. Okay, so this ounce converted to grams, I'm going to just use the top numbers, which is 2 grams is 2 ounces is 58 grams. So this is 2 ounces is 58 grams. The goal is to cancel out the units. So teaspoons and teaspoons will cancel, ounces will cancel out. I'm actually going to need a calculator for this one. But I have successfully gotten to the units I want, which are grams. That's grams or G. And so this is going to be multiplying across. Multiplying across is going to be 2 times 1/2 times divided by 3 divided by 2. So I get 9.6666 and so on. And so this I'm going to round because the original number, 2 teaspoons, has 1 sig fig. Remember that. Anytime you go to a calculator, you want to make sure you round to the correct sig figs. And so this to have 1 sig fig, I'm going to round up to 10 grams. This number has 1 sig fig because remember that the trailing 0, that 0 in the 10, is not significant because there's not a decimal there. So that has 1 sig fig, same as the original number value. Sound good? Okay, so this is going to be the most common type of conversions you'll do moving forward. And I got to tell you, I do conversions all the time when I'm using a recipe, mostly because it's like ounces to cups. Like it'll tell you how many cups you need of, let's say, chicken broth, but I have the ounces on the chicken broth to figure that out. Even sometimes when you're at the store to understand exactly what you need to buy. That is, so let's take a look at how those calories are calculated from the information on the nutrition facts label. So this is talking about the macronutrients in food. So food can be broken down into its components. The majority of what food is made out of is these components: the fat, carbohydrate, and protein. That provides all the energy. So all the energy and most of the raw materials. So you eat food so you can break it down. When you break the bonds, you get energy in the form of calories, or energy measured as calories. And then you also break it down and you get those parts, and those parts that can then be used in your metabolism to make other things. For instance, you eat protein, and then your body needs those parts to make protein in your body. So that's all needed for the process of living, which is called human metabolism. That's energy and life in humans. So food is really a form of chemical energy. So we had the 5 major forms of energy, and chemical energy is when you get energy from bonds. So bonds are broken, new bonds are formed in a chemical reaction. And what we're talking about in food or metabolism is the breaking of bonds in the process of digestion. Okay, so you get that chemical energy from food, and it is converted into mostly radiant energy. That's to heat the human body. So radiant can be heat and light. So radiant energy to heat the body, and also mechanical energy to move around. That includes muscles, but also smaller scale at the microscopic, submicroscopic level, moving things around in your body, like nerve impulses. So that's radiant energy is the majority of why we eat, is to heat up your body and keep it at this 98.6. That's what all the biochemical reactions in your body evolved to operate at this warmer temperature. So, you probably heard that about humans being warm-blooded mammals. We have warmer temperatures. So that is basically this homeostasis that the human body has established. And it is why you need constantly to keep your body warm, so that these reactions all happen that keep you alive. Okay, so the macronutrients are in the food, and that provides the energy that is measured in calories. Those are nutritional calories, which is the uppercase C, which is equal to 1,000 lowercase c calories. So 1 calorie, I mentioned in the video, is equal to 1,000 or 1 kilocalories of the lowercase c. So there's a distinction between the uppercase C, which is a nutritional calorie, compared to the lowercase c, which is how calories or how they're measured in a chemistry lab. So fat, carbohydrate, and protein, when you break down fat, when you break down carbohydrate, when you break down protein, you get energy from the bonds. And fat is 9 calories per gram compared to carbohydrate and protein, which is each 4 calories per gram. So we can see the number that is the total calories is 150. And we can figure out the total calories also from calculations using the fat, carbohydrate, and protein. Okay, so basically I'm going to use this like the answer key. The total calories is given. Yes, we already have that, but we want to calculate it now. So use the total fat, where the mass of the fat is 10 grams. Okay, and then you have the fat provides 9 calories per gram. So this is a conversion of 9 calories per gram of fat. And so the grams and grams will cancel out. And then you'll have here the calories of fat. So that's 90 calories that you get from fat, and that's the uppercase C. Okay. For carbohydrates, so looking at total mass of carbohydrates, this is 13 grams. 13 grams of carbs, carbohydrates, and carbohydrates provide 4 calories per gram. So this again is a conversion of 4 calories per gram of carbohydrate. And so the grams will cancel out, and we'll be left with the carbs, or the calories from the carbs. And I need my calculator again for this. So this is going to be 13 times 4, or 52 calories. And those are 52 calories from carbohydrate. But remember, the distinction of where did those calories come from is actually not important anymore. So even though this label shows the old-fashioned idea of calories from fat, it's actually does the calories came from. Calories are calories. Okay. So this is protein, which is not written as total protein, but it is the total protein. That you have 2 grams of protein. And protein will also provide 4 calories per gram. So 4 calories per gram, the grams will cancel out. And then you have 8 calories from protein. Adding all that up, so 90 plus 52 plus 8 is adding up to 150 calories. So that does match calorie count on this label. You will find, though, when you do your own calorie calculation, go find a label that often does not match exactly. And that's usually from rounding. So you can round up usually to the total calories, and it shouldn't be too far off, but you are going to calculate that as part of this week's discussion. Okay, so do calories, answering this question down here, do calories from fat provide a different type of energy than the calories from carbohydrates? And the answer is no. So calories are all the same. They're just units of energy. And they're the chemical energy that you get from the bonds in food or any chemical compound. Right? Because we can get chemical energy from breaking the bonds in any chemical compound. And that's what you see in a chemical reaction is you get chemical energy from a reaction. So the calories from food are breaking the bonds in the process of digestion, and it's measured in the, though, if they're calories from fat or calories from carbs or calories from protein. Calories from fat are listed separately. The reason is this is for people, individuals, let's say individuals that are on a fat restricted diet. And the reason why people might be on a fat restricted diet is not from the calories, but it's from the fat itself. And we're going to talk about that is because saturated fats, we'll get into that, can lead to heart disease. That's not heat disease, it's heart disease. And so this can lead to blocked arteries, heart disease, and heart attack. Also stroke, basically, when you block an artery. Okay, and so we'll get to that in talking about what are called saturated fats compared to unsaturated fats, and all types of fats we'll get to right now. So this is when certain individuals are paying attention to their fat intake, basically the breakdown of fats that they're allowed to have, they will be guided by the calories from fat. Or specifically looking at the label, you can look at fat or trans fat. Okay, and so that is kind of an old-fashioned notion that calories are different if they're coming from fat or from carb or from protein. They are exactly the same. Okay. So have you heard of that concept of healthy fats versus unhealthy fats? It is based on the chemistry of the molecules, of exactly what those shapes of those molecules. And we're going to start looking at these molecules that are organic molecules, as I mentioned. They are carbon-containing compounds. And because they're just carbons and hydrogens, we have what's called the line angle drawing. So the line angle drawing just shows a bunch of zigzag lines. And so for someone who's not familiar with chemistry, it looks like a zigzag line. But since you are familiar with chemistry, it's not a zigzag line. They are carbons and hydrogens. So going back to the shirt I'm wearing today, this one, that was the structure of theobromine. We're going to be seeing a lot more of these, which are organic molecules, which have just lines. And it's at the intersections of lines where those intersections are carbons. And that's what we start with, is looking at the fatty acids, which have that look like zigzag lines, but these are called the line angle drawings, are representing carbons, hydrogens, and then the other atoms you have to write in, like the oxygen, which is not carbon or hydrogen. Or if you have a nitrogen, you have to write in an N because it's not carbon or hydrogen. Okay, so the line angle drawings are just for carbons, which are the ends of lines or where two lines intersect. So let's take a look at the starting first is the fats and oils. So fats and oils are generally, they're the same family. They're the family of lipids. And lipids are in foods, but also not in foods. So see steroids, which are, we're going to get to in drugs. So fats and oils, what they have in common is they just have a lot of carbons and hydrogens. There's some other atoms in there, like this one, we can already see the structure has some oxygens in there, but they're mostly carbons and hydrogens. So fats are usually going to be solid at room temperature and also originate from animal sources like butter. There's also oils that are usually going to be liquids at room temperature. And there also are coming from so not from animal sources, but from plant sources. So olive oil is an example. Another example, though, is coconut oil. Have you ever worked with or seen coconut oil? So coconut oil is interesting because it's a plant source. You know, you have the coconut tree, and it comes from the fruit. The coconut oil is pressed from coconut oil can be a solid at room temperature. And that solid coconut oil is a good replacement for butter in baking. So it's used in baking for vegan recipes to replace butter, but it is not always, that's why I have usually oils are liquid at room temperature. Coconut oil is almost always a fat at room temperature, and it does depend on the temperature. Okay, so we have these fats and oils. What they have in common is that they are in the lipid family, and they're also called triglycerides. And that's because of what they're composed of is that you have a glycerol, which is glycerol. Let's write the structure on here. Glycerol is 3 carbons that are bonded together with single bonds. And then there are 3 OH groups, and you can draw it down, up, and down. And then the rest of the molecule is, but this is for short, the line angle drawing would look like this, 1, 2, 3, with down, up, and down. And then you could fill this in with 3 carbons, 3 OH groups, and you can fill it all in with hydrogen. So you'll see different representations of this, which is called the glycerol molecule. So when you start with a glycerol molecule, you add 3 fatty acids, and that's called a triglyceride. Okay, so the fats and oils contain these fatty acids. Now let's look at the structures of the fatty acids, which is one component. When you put together 3 fatty acids and on the glycerol molecule, you'll get what's called a triglyceride. Okay, so the fatty acids are, this is the first, which is called a saturated fatty acid. So remember, this is called the line angle drawing. When you have the end of a line or where 2 lines meet, that represents a carbon. And so we can count this. There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. That's 18 carbons total. And then this group, which is called the COOH group, that's called the carboxylic acid group. It's all those atoms bonded together, the double bond oxygen and the single bond oxygen. They have a function. And we're going to get to talking more about these when you have a bunch of atoms bonded together in biochemistry that works together having a function. It's called a functional group. So this is an example of a functional group. That's just a little preview. We have a lot going on for functional groups. It's a functional group. We have a lot going on for functional groups. This is a preview, but there we'll have more. You'll see it again in module 12. So for this molecule, this saturated fatty acid is a zigzag line, but the overall shape is really a thick, straight shape. Okay, so this part of it, which is, nope, don't want that. This part of it, nope, don't want that. Okay, let's try this. This part of it, there we go. Okay, so that's the hydrocarbon part. This is the hydrocarbon tail, is all just single bonds. And when they are all single bonds, you have an overall straight shape. Even though it's a zigzag line, when you actually fill that in with the atoms, that's the space filling or molecular view, it's really just a thick zigzag line that thickens out. So it's really a straight shape. And so what happens when you have a bunch of these straight molecules? They will stack up. Okay, and so when these straight molecules will stack up, And when they stack up, they form a solid at room temperature. So they will also stack up in the walls of your arteries. And that leads to stacking up and in the walls, the internal walls of your arteries. Specifically, if it stacks up in the internal wall of your cardiac artery, that will lead to a plaque formation, and a plaque or a blockage. And when you have the blood flow blocked to that cardiac artery, it leads to a heart attack. So this is no good. And that's why saturated fat, or heart attack or a stroke, both of those can happen. Saturated fats are considered unhealthy fats because these fats, which starting with the shape, they're all single bonds and they're straight. So because they'll stack up, either becoming a solid at room temperature, that's your butter or your coconut oil, they'll stack up and be a solid, or in your arteries, they'll stack up and lead to a blockage. So that's an unhealthy fat because they will stack up. So let's go down and look at this other shape though. When you have one or more single bonds, you're talking about an unsaturated fat. So an unsaturated fat is one or more double bonds. Did I say single bonds? When you have one or more double bonds, that's unsaturated. So having a double bond present causes the shape to be different. So this shape is due to a double bond with what's called a cis arrangement. In the cis arrangement, the cis arrangement has the hydrogens are on one side of the double bond. They're both on the one side, and so it leads to a bent shape. So the overall shape of this molecule, instead of being straight, it's not going to be straight, but it is an overall bent shape. So see how it's bent or it's curved? It makes this C shape. And this is the cis arrangement of that double bond. You have, this is the double bond. And because the hydrogens are both on one side, it forces the hydrocarbon tail to bend around when the hydrogens are just on the one side. And so what happens when it is bent is this will not stack up. And when these molecules are C-shaped, when they're curved, they won't stack up. What they do is they flow over each other and become a liquid. And so that's a liquid at room temperature. And so because they don't stack up, this is called a cis fat. Because they don't stack up, they won't stack up in your arteries. And if they don't stack up in your arteries, you're not going to have that plaque, you're not going to have the blockage, and you have a healthy fat as a result. So one example of this monounsaturated, where you have one double bond, that this is be a solid that's going to be a liquid at room temperature, is olive oil. Olive oil has a lot of these monounsaturated fatty acids in there. Now, here's another possibility, though. If you have the monounsaturated, so monounsaturated means one, mono is one, and unsaturated means double bond. So if you have one double bond in a different shape, which is called the trans arrangement. So the trans arrangement has the hydrogens in the double bond on opposite sides. When you have those two hydrogens on the opposite sides of the double bond, so there's the two hydrogens there, it leads to this overall shape, which is very similar to the first. This is an overall straight shape. Notice this, zooming out. This is a overall straight shape here. This one, overall straight shape in red, compared to this overall bent shape of the cis arrangement. And so this is also an overall straight shape. This doesn't curve or bend down. So what happens when you have that overall straight shape is that you have, this does affect the ability to form a solid because the overall straight shape can stack up. And what this does is it forms a solid at room temperature. And when you have a solid at room temperature, that is what leads to this looking like butter or coconut oil. And this also, what this does in the body is this can stack up in your arteries and form that plaque. And this forms plaques leading to blockages. And plaques and blockages are no good. They can lead to heart attack and stroke. And so this is an unhealthy fat. Okay, so yes, this is an unhealthy fat, and it comes from the chemistry of it. This is not all single bonds, but because this double bond, this trans double bond, leads to an overall straight shape because of the nature of the molecule, this will stack up and be exactly like, almost exactly like the saturated fat. Okay, so this is similar to the saturated fat. So here's the thing, is both of these, zooming out a little bit, both here, we looked at the monounsaturated fatty acid with the cis arrangement and the monounsaturated fatty acid with the trans arrangement. Both of them are one double bond. So that's what monounsaturated means. It means one double bond. And it really depends on what's going on with that double bond. Is it a cis double bond or a trans double bond? And so because of the difference, we cannot say that any monounsaturated fat is an unhealthy fat. So we know that the cis fat is a healthy fat. Why it's healthy is because it's bent, okay? And that bent shape doesn't stack up. Compared to the trans double bond, a trans fat is unhealthy. And the reason why it's unhealthy is because there's an overall straight shape, and that can stack up. So going back, I'll let you write all that down. Going back to what you see on a nutrition facts label is going back to here. On a nutrition facts label, when you're given the total fat, let's erase some of this here, you also will see fat or trans fat. And so that's because those types of fats are unhealthy. These are your unhealthy fats. And they will be listed on your nutrition facts label. The saturated fat and trans fat do the same thing. They have an overall straight shape and they'll stack up. And so that's why you don't need to look at the calories from fat. If you understand the nutrition facts label, you can look for the fats that are unhealthy, which are the saturated fats and trans fats. And they're reported by law on the nutrition facts label. Now, most foods do not have saturated fats and trans fats. What foods do are chips. So I'm actually going to take a look at this one on my Oreo cookie. There are saturated fats on there. So there's 2 grams of saturated fat. And so it is something to pay attention to if you are on a fat restricted diet and you are trying to lower basically you're prone to heart disease or plaque buildup in your cardiac artery. I know some people have already had a heart attack, even at young ages, and they are supposed to pay attention to their saturated and trans fats. And basically, this is a food that will break down, and those fats will be in your bloodstream, and you don't want to have the bad fats. So those are the bad fats, the unhealthy fats. Those are the saturated fats and trans fats that lead to the blockages and heart disease and stroke. Okay, so you could take a look at that when you take a look at your nutrition facts label for this week's discussion.